What is entropy? In physics, we like specific definitions, which is why calling entropy the amount of disorder seems weird. Weird, but true. A gas has more entropy than a solid. Its particles are more disordered. So entropy has something to do with temperature, and that is what this equation says, in part. Well, thank you, Rudolf Clausius, for this equation. We'll develop it in part 2. But hey, it's a big job, so we'll need lots of tools, and that's what this video is about, getting the tools to develop this equation. In part 3, we'll tackle this equation, which is even stranger. What is multiplicity? So we have 3 videos here to try to make sense out of disorder. And apparently nature loves disorder. That's what the second law of thermodynamics says. Entropy increases over time. You can see it as a gas diffuses, or as a solid dissolves. Nature tends towards more disorder. That's why heat flows from a higher temperature to a lower temperature. More on that later. But speaking of heat, it is released in this chemical reaction. Again, disorder obviously increases. Nature is biased in that direction, and that kind of makes sense to me, like ping pong balls on a shelf. Shake up the shelf and they will tend to fall over the lip and off the shelf. But not all reactions work this way. Something as common as baking soda and vinegar will do the opposite. It will absorb heat, it will feel cool. And this reaction, just like the explosion, it's spontaneous. Well, why is that? Go ask a chemist. Our point here is that there must be a different type of energy, some sort of hidden energy, not just heat. One more thing before we get started. Although nature tends to act towards more disorder, it is possible, sometimes, to put work or energy into a system to increase the order. So it's not exactly the same thing, but we'll see what nature's reversible changes can tell us about nature's preferred changes, about entropy. Now, on to the equations. To tackle the second law of thermodynamics, we'll need the first. Energy is conserved. Delta E equals delta W plus delta Q. In short, there are 2 different ways to change the temperature or the thermal energy of a system. You could add heat to it, fire. That's not surprising. But you could also do work on the system. You could stir the water. Ask James Joule about that one. That would speed up the molecules and increase the temperature. And if you don't believe me, grab a blender and a thermometer and try it yourself. The first law. Next, the ideal gas law. PV equals nRT. Rolls off the tongue. And we will focus on ideal gases because they have the best equations. Like this one. The equation for thermal energy. Look, proportional to temperature. Finally, an equation for heat. Q equals mc delta T, ideal gas style. Speaking of gas, we'll describe its behavior on a pressure versus volume graph. Get used to these things, you'll see them a lot. And what do we mean by behavior? This, heating at constant volume, temperature increases. Or this, heating at a constant pressure, temperature and volume increase. You could cool off the gas instead of heating it if you wanted to. It works in both directions. This one is a little bit more complex. Adiabatic compression. Temperature goes up, but by definition, delta Q is 0. Push that piston down so fast that no heat can enter. Do work on the gas and increase its energy. Now that's weird to say. It's weird to say that the temperature is increasing even though there is no heat added. But hey, that's what the first law is all about. Next, isothermal. Temperature stays the same. So what's up with that bucket of ice? Well, if we're compressing the gas, we'd expect the temperature to increase, unless delta Q is negative. That's the ice. Delta W is positive. It's a compression. Delta Q is negative. We're taking heat out, and delta E is 0, isothermal. And we can calculate how much work is being done by finding the area under the PV curve. Pressure, if you remember, is force per area. That means P delta V has the same units as F delta X. Now, I don't want to argue about negative signs. Don't be alarmed by the negative. We already said that that's what you'd expect. Compressed gases increase in temperature. Expanding gases cool off. That happens in chemistry and on mountains. At the top of this mountain, we have low pressure, low temperature, expanded gas, less dissolved water vapor. So we agree that ignoring delta Q compression always means higher temperature. Ignoring delta Q compression means higher temperature, and that explains the negative. Volume goes down, thermal energy goes up. But negatives are annoying, they really are. You could be talking about the work done, quote, by the gas on its surroundings, or the work done by the system, quote, on the gas, and you get a headache. Moving on. Negatives really are annoying, but finding area with integration, that is fun, especially if it involves a natural logarithm. You'll see more of these too, but wait a minute. Why all this stuff about gases? I thought we were talking about entropy. We are working again. What are we doing? We're working our way towards Clausius's equation, delta S equals delta Q over T. But we'll need all this stuff in order to derive that equation, trust me, including this. See the asterisk? This is true for adiabatic, no heat processes. Delta Q is 0. And what the heck is gamma? If you don't care about where these things come from, just skip over to video 2. But for those of you who need to prove everything, we'll be starting with molar specific heat of a gas at constant volume. None of that expansion nonsense. Hey look, it's the first law of thermodynamics and the ideal gas law. They're working together. Nice. Next, molar specific heat of a gas at constant pressure. This time, the gas expands, and that makes the heat capacity higher. It takes more energy to increase the temperature of the gas because you're allowing it to expand and do work on the environment. Cp is greater than Cv. And that's what the weird gamma term is. It's a ratio of heat capacity. Seems useless, but it will come into play here. And this is just what we're trying to prove. Adiabatic processes only. By going back to basics and taking a derivative. 3/2 R. I've seen that. 3/2 R. I know that's Cv. Neat. Note that this expression works for all processes, not just constant volume. This expansion, on the other hand, this is adiabatic only. Again, no arguing about negatives. I know. Let's put these two guys together. Good. PV equals nRT. Substitute. Rearrange. This is a bit wacky, but you can trust my algebra, I think. Let's bring CP into the party. How can we do that? Oh, that's how we can do that. The old R plug-in subtraction trick. Got it? We're almost done. We're almost done because of division, and because of the definition of gamma, and substitution, and integration. I told you to get ready for more natural logarithms, and here they are. This proves that t times v to the gamma minus 1 is a constant. And if you don't believe me, then this slide might help. Or maybe not. Anyway, let's use it. Again, adiabatic only. But that's the problem. I don't want to just talk about adiabatic compressions and expansions of an ideal. I want to talk about everything. I want to talk about why some natural processes are reversible, like swinging the pendulum or a phase change, and some processes are irreversible. That's what I'm concerned with. And that's what Nicolas Carnot was curious about too. He invented as a thought experiment an ideal, reversible engine, and that's what we'll use in part 2. But not just to go around in circles. This is where we're going. Clausius's equation for entropy.